All right, so welcome to page 6 of our packet. This is looking at types of radioactive decay. So when we say a sample is radioactive, that means it's breaking down over time by essentially spitting out radioactive pieces of itself. And so for types of radioactive decay, there's 3 different types of radioactive decay, 3 different types of pieces that this element can spit out of itself. There are actually more than just 3, but there's 3 main ones that are the ones that we focus on in our class. So a couple of definitions and terms to take care of first. So radioactivity is the spontaneous disintegration of an atom's nucleus. So spontaneous just means it's kind of happening randomly over time. And then nuclear chemistry is all about the nucleus of the atom. The nucleus is where the protons and the neutrons are located. And so if we have a radioactive atom, it's really the nucleus of the atom that's radioactive. The reason why an element will go through radioactive decay is because it's unstable. The amount of protons and neutrons that are together in the nucleus just isn't a good ratio. And so that nucleus is going to spit out chunks in order to try to become more stable. Just as a reminder, we write our element symbols like this when we're talking about nuclear chemistry. This is our element symbol. This is our mass number on the top. And then our bottom number, that is the wrong direction for an arrowhead. Our bottom number is our atomic number, which is our number of protons. Okay, so this is the number of protons, and our mass number is the number of protons and neutrons added together. So that's a review of what we saw on page 3 and 4. From here, 3 types of nuclear decay. Our first type of nuclear decay is called alpha decay. So this is named after the Greek letter alpha. So it can be written kind of like this. That's the Greek letter alpha. So if you see that, that is what that means. And I see it on here a couple times. So this is that alpha symbol right here. So it's just kind of a shorthand way of writing alpha. What happens with alpha decay is the nucleus spits out what's called an alpha particle, and an alpha particle is 2 protons and 2 neutrons that are combined together. If we think about what element that is, the element that has 2 protons is helium, and then because it has 2 neutrons, 2 plus 2 gives us the mass of 4. So what this really is it's really just a little chunk of the nucleus that gets spit out that looks like helium. Okay, so the helium nucleus, 2 protons, 2 neutrons, gets split off of the atom. You're going to see that as we look at the 3 types of decay, the alpha particle, even though this is pretty small, 2 protons and 2 neutrons, doesn't seem like a lot, this is actually the largest. So this is the largest type of nuclear decay. And because it's really large, that means that it can't really fit through small little openings. It gets stopped. And so this is going to make it easier to stop. So if you have alpha particles coming at you and you have, your packet and you hold up, a piece of paper that's maybe 10 pages or so, and you hold that up, that's actually enough to slow down and stop the alpha particles so they can't get to you. This is going to make alpha radiation the least dangerous out of these 3 types. Alpha particles are not great for you, so it's not like, go sit in an alpha room or something. But alpha particles tend to do the most damage to the skin because they can hit your skin, but they're not going to go farther. They're not going to hurt your organs so much because they can't go through your skin. Alpha particles can also do lung damage. If you inhale something that has alpha particles, those get into your lungs and then they can do lung damage. But besides those 2 types of damage from alpha particles, it's hard for them to get into your body. If you ate something that had alpha particles, they can get into your stomach, and in that case, they could get into your organs as well. But again, your skin is kind of a good barrier to protect you from alpha particles in general. All right, so for alpha particles, the way that we would write the symbol for this, we can write it 2 ways, either as He, because it's helium, 2 protons, the atomic number goes on the bottom, and then the mass number, 2 protons and 2 neutrons, 2 plus 2 is 4, would go on the top. You could also write this as 4, 2, and then that alpha symbol instead of HE. So that's totally a personal preference which way you prefer to write it. I'm going to write HE instead of the alpha symbol. Our general formula for an alpha decay, we're going to start with some sort of radioactive material. So we would write the symbol for the radioactive substance. And it's going to decay, meaning it's going to break apart. So I start with this one radioactive element. We draw an arrow, which basically means becomes or turns into, and it's going to break into two pieces. It's going to break into this alpha particle that we just wrote the symbol for over here, and then it's going to break into another piece. And I'm just leaving these boxes blank for now because I don't really know what goes in here. That depends on the specific problem. But this is our general form. One thing breaks apart into an alpha particle and something else. In our first example, this says AC-225 is directed to cancer cells, which are then destroyed by this alpha radiation. We're going to write the nuclear equation for the loss of an alpha particle from actinium-225. Actinium-225 is our starting radioactive substance. So I'm going to start by writing its symbol, AC. When we have it written with a dash in the number, this is our mass number. Mass number always goes at the top, so 225 goes up top. And the bottom number is the number of protons, or the atomic number, which I can look up on the periodic table. So if I find actinium, its atomic number is 89. Notice that on here it says the mass is 227, and yet the mass that we're using is 225. That's because that's this version of actinium. It might not be the most common form of actinium, but this is the form that is radioactive in this problem. I'm going to write down that 89 that I looked up on the periodic table. So that's this first piece. It's now going to break apart, and the first thing that's going to get spit out of this nucleus is the alpha particle. Okay, so this nucleus right now had 89 protons. It's going to take 2 of them and spit them out, and it's going to take 2 neutrons and spit that out as well. In order to figure out what we're left with, when this nucleus takes a tiny chunk of itself and spits it out, we have to do addition subtraction. Okay. I'm going to look at the top part of this. This is essentially just a math problem where the arrow is like an equal sign. The mass before was 225. That's equal to the mass of 4 that got spit out and what's left over still in the nucleus. So I just need to think about what number, when I add 4 to it, would become 225. And that's 221. 221 plus 4 is 225. I'm going to do the same thing on the bottom. 89 is equal to 2 plus how many? So if we spit out, we had 89 protons before, we spit out 2 of them, how many are still there? That would be 87. 87 plus 2 is 89. The last thing we need to do is figure out what element this is. So I'm going to find the element that has 87 for its atomic number, and that is Fr, which is francium. So francium is what we have now. When actinium goes through radioactive decay, it spits out a chunk of itself, and then what's left becomes francium. So it's actually converting from one element into another through radioactive decay. All right, so I'm going to leave this one for you to try, and I will scan this so that you have a way to check your answer. But same basic process, starting with thorium-230, alpha particle is one of our products, doing addition subtraction to find the other one. The next type of decay is called beta decay. And beta is a Greek letter that looks like a B. It just has a curly tail on the end of it. And so what beta decay is beta decay is when the nucleus spits out an electron this time. An electron is much smaller than 2 protons and 2 neutrons. So this is going to be something that's smaller in size than what we saw for alpha. Because it's smaller in size, now it can actually go through materials more easily because it's really teeny tiny and it can fit through crevices. And so this is going to be harder to stop. I'm going to write that it's medium to stop because it's not the hardest one of the three to stop. And this is going to make beta particles have a medium amount of danger of the three. One note, it might be kind of weird that I just said the nucleus spits out an electron because there aren't any electrons in the nucleus. The nucleus actually creates an electron and then gets rid of it. And that's a complicated process that we're kind of skipping over a little bit here. All right, so two ways to write the beta particle. I can write an E for an electron, that's what I'm going to write, or you can write the beta symbol, the B with the curly tail. The number on the top should be the mass number. So the mass of an electron, we've said up to this point, electrons don't have any mass. So we have 0 for the mass number. The number on the bottom is the atomic number, which is the number of protons. An electron isn't a proton. It's kind of the opposite of a proton. Instead of being a charge of +1, it has a charge of -1. And so that's actually the number that we write on the bottom. -1 would go down there. Our general formula for a beta decay is going to look pretty similar to what we had before. We have something that's radioactive, so that's going to be our first piece. It's going to spit out a beta particle, and then we have something else that's left over. The beta particle we would write as that 0, -1e, and then there's some other piece. And these two pieces I'm leaving blank for now, they depend on the question. Our example on here, to treat cancer, wire containing iridium-192 can be implanted into a tumor. This then decays by beta emission, killing the cancer cells. Balance the nuclear equation for the loss of a beta particle from this radioisotope. So we're going to go ahead and start with this iridium-192. I need to find iridium on the periodic table. So iridium is this, symbol is IR, and its atomic number is 77. Okay, so IR, atomic number goes on the bottom. The mass number, I'm going to use what's given to me in the problem, not what's on the periodic table, because not every form of an element, an isotope of an element is radioactive. So I have to make sure I'm using the one that the problem says is radioactive. This is going to decay. It's going to lose a beta particle. So I'm going to write my formula for the beta particle, 0, -1e. And then from here, again, I have to do my addition subtraction. The top part's going to be pretty easy because there's a 0. 192 equals 0 plus 192. Right? Any number plus 0 is the same thing. On the bottom, however, the math is a little bit trickier this time. 77 is equal to -1 plus something. -1 really means subtracting 1. So I'm looking for what number, when I subtract 1, gets me 77. And so the number that I would subtract 1 from to get 77 is going to be 78. So a lot of times it's common for people to want to put 76, and then a -1 would get us 75, not 77. Once we have this, we're going to find element 78 on the periodic table. That is platinum, Pt, which would be our symbol. That would go here. All right. The next one, same thing as before. I'll have you try this one, and I'll post the scanned page that will have those filled in. Third type of decay is called gamma decay. So if you notice these three types, they were alphabetical order. We had alpha A, beta B. Be nice if we had C, but it's G this time. Gamma decay, the symbol kind of looks like this. We're not going to use it a lot, so it's not super important to recognize the symbol for gamma. Gamma decay is when the nucleus is going to spit out energy. It's actually not a particle at all. It's just a wave. Basically, that nucleus is just rattling around. It has too much energy, and it's just going to release some energy. Kind of like a little kid who is having all this energy, runs around the room, burns off some of that energy, and then can sit down and relax. So the gamma energy is just energy spit out to make that nucleus have a more stable form. Gamma radiation is pure energy. It is very difficult to stop because it's just pure energy. It's kind of like a microwave that you use to cook food in the microwave oven. It's just even higher energy than that. Because it's very difficult to stop, it is the most dangerous form of radioactive decay. So this is the one that is the most dangerous overall. It could go through your skin, it can go straight into your organs. So this is the one that you couldn't block by just holding up a piece of paper. Gamma decay doesn't change particles in the nucleus, however. Right? We're not spitting out protons or neutrons or electrons. We're just changing the amount of energy of the nucleus. We don't write equations for these ones because literally the equation would say whatever we started with turns into the same thing but a lower energy form. So there's no point in saying, radioactive iodine releases a gamma ray and it's still iodine and none of the numbers have changed in the problem. Okay. One more thing I'm going to add on here is just how would we stop each of these types of decay if we were trying to, right? So for alpha decay, we said it's the easiest to stop. Alpha decay can be stopped by paper or clothing. So we would actually be able to prevent alpha radiation from, getting into your body with pretty thin materials overall. For beta decay could be stopped by thicker materials, so like really thick amounts of paper, like textbook thickness of paper, or like really heavy duty or thicker types of clothing, even thin amounts of metal. And then our last one on here, gamma decay. Gamma decay is the hardest to stop. Gamma decay could be stopped, but only by really thick concrete or lead. So we would want thick concrete or thick lead. So when I say thick concrete, we're talking like maybe 3 feet thick or more. When I say lead, we're not talking about, aluminum foil type piece of lead. Like we're still talking about a pretty thick piece of lead overall. But that's kind of the difference, like this piece of paper, if I said, what could having just a couple pieces of paper potentially stop? Alpha particles are the only ones that it could stop. But if I had, 10 feet of concrete, that could stop all of them. All right, that's your introduction to types of decay.